Welcome to CAPP. We are very pleased and excited to have you here. We'll guide you to our unique facility in this virtual tour. Our research consists of two main topics. One, Axion dark matter, and second, high-precision physics using particle accelerators. Both our subjects are related through a common question regarding the origin and fate of our universe. Dark matter is a mysterious substance holding our solar system and all the stars together in the Milky Way. Here at CAPP, we have invested in human ingenuity and have developed some of the most amazing techniques to be able to finally answer whether axions are part of the dark matter mystery. Dr. Woo-Hyun Chang is going to tell you more about our exciting discoveries that make it possible to answer these fundamental questions.
With first three systems, CAP-ACE, CAP-ATV, and CAP-MC, we have already excluded three different mass ranges of the Axion as prototype experiments. Two of them used identical top-of-the-line dilution refrigerators that provide less than 10 millikelvin base temperatures. CAP-ACE is the first complete Axion search experiment built in Korea. It has an 8 Tesla superconducting magnet of 125 mm clear bore and used for searching for axions around 2.6 GHz in 2018. CAP-ATV is a basically identical experiment, but equipped with a larger bore 8 Tesla magnet, 165 mm bore. Therefore, its natural frequency is lower than the previous system. This experiment has searched the axion around 1.6 GHz in 2019. The last prototype experiment was with a wet helium-3 refrigerator capable of 2 Kelvin temperature. This is the first Axion experiment employing a multi-cell cavity and has searched the axion around 3.2 GHz in 2020. All those pilot experiments were done with the traditional HEMT amplifiers that gives relatively high system noise temperature. To reduce it as much as possible, employing quantum noise limited amplifiers is critical. Dr. Sergey Uchaykin will tell you about how we are developing the device at the center.
Traditional HEMT amplifiers have high intrinsic noise that is a main bottleneck in the Axion search experiment. With quantum limit noise amplifier, the experimental noise can be drastically reduced, therefore increase the experiment performance phenomenally. We are developing various quantum limit noise amplifiers by collaborating with top world experts. For the best performance of amplifiers, our collaboration uses a few top modern technologies, such as nanotechnology to fabricate superconductor chips, dry dilution fridges to achieve operation temperature in millikelvin range, and the top microwave components and equipment to test and characterize them. As a result, we received a number of amplifiers with a record noise characteristic in the frequency range of 1 to 6 GHz and implemented them in 5 experiments in our center.
Another major breakthrough in the Axion search experiment is superconducting cavities and high-frequency resonators. Dr. Sung-Woo Yoon will introduce you to our cavity R&D program.
Searching for axion is a bit like tuning a radio. You turn the knob until you pick up the right signal. A microwave cavity is our axion radio, where we take advantage of the resonant effect. To enhance the effect, we adopt the superconducting technology. For this purpose, our center is equipped with a specialized system for uniform deposition of superconducting material on the inner surface of a cavity. We are also developing various designs to apply the second generation high temperature superconductors, which maintains the superconductivity in the presence of a strong magnetic field. Now the technique is fairly mature, and our center plays a leading role in developing superconducting cavities. In the meantime, we also come up with new ideas to extend the search range to even higher frequencies. Our research team has devised an interesting cavity design, dubbed pizza cavity, which is featured by a sliced pizza-like arrangement of partitions. This structure enables us to access high-frequency regions with the full use of a given detection volume, which will speed up the search process manifold. Currently, 2 multi-sliced pizza cavities are in place to search for high-frequency actions. We also designed unique metamaterial structures to exploit higher-order resonant modes and to approach even higher frequencies with improved performance. All these pioneering efforts are expected to create critical impact on the next generation of Axion searches. Before we build such sophisticated and delicate systems, we carefully study their properties and feasibility by relying on simulations. The center has 3 different software and 4 high-performance workstations dedicated to simulation modeling. The final designs are chosen based on various independent studies and verified by making and testing prototypes.
All those R&D efforts for innovations and breakthroughs will be focused on our flagship experiment, CAP12TV. Dr. Byung-Ro Ko will tell you more about it.
Welcome to the CAPP12TV site. As you were told earlier, they are calling CAPP12TV the flagship experiment of the center, because all the experimental parameters have been pushed to reach state of the art. One of them is the superconducting magnet, whose bore diameter 320 mm and field strength is 12 Tesla, which is unique equipment in the world. This world unique magnet will produce the strongest action signal power if actions are there, together with the dilution bridge that can cool the experiment down to about 50 millikelvin. CAPP12TV will be a DFSG action definitive search experiment. Once it is realized, we will be ruling the community. You better keep staying tuned.
We have some of the very best Axion search experiments based on resonant cavities. In addition to them, we are also doing non-cavity Axion experiments, Axion and Gnome. Dr. Yoon Shin will tell you about them.
Axion and Gnomes are tabletop experiments, but they are complementary to holoscope experiment. Dr. Andrei Metlashov will explain Ariadne in more details.
In Ariadne, axions mediate long-range interactions between polarized helium-3 atoms and tungsten mass. The experiment can test high axion mass range from one single measurement. CAPP, we are developing helium-3 polarization system, also superconducting thin film shielding, and also ultra-low noise squid-based gradiometers.
Gnome is now looking for entirely different class of dark matter called Axion domain world. Gnome utilized optical magnetometers for this search, but instead of just one magnetometer, Gnome has a network of optical magnetometers all over the world, including CAPP. CAPP is now actively searching for Axion domain world with our state-of-the-art cesium magnetometer.
For the precision physics research, we are participating in large-scale experiments using particle accelerators, proton electric dipole moment, muon G-2, and a comet. Meet Dr. On Kim. He will give you an idea about our precision physics research.
There have been efforts to measure an electric dipole moment, often abbreviated as EDM, of fundamental particle and nucleons for decades. A non-zero nuclear EDM directly indicates strong CP violation, which has never been found on the list.
We are playing a leading role in building conceptual and technical designs of realistic storage rings for the proton-neutron EDM experiment, and making breakthroughs to achieve an unprecedented precision.
The muon G-2 experiment aims to measure the magnetic dipole moment of the muon to an extremely high precision To unveil a long-standing mystery in particle physics, the standard model estimation of how fast the muon wobbles in a magnetic field doesn't seem to fully explain the measurement.
We have been active international collaborators of all muon G-2 experiments in the world, one at Fermilab in USA and the other at JPAR in Japan. Our main contributions include extensive studies on systematic uncertainties. We are also participating in an experiment searching for charged lepton flavor violation with muons, which will be the strongest evidence of physics beyond the standard model. The COMET experiment is now under construction of beamlines and other infrastructures in JPAR. We are actively involved in many parts of the experiment, especially focusing on the trigger system development, as you can see here.
We are also leading the physics study for the muon to positron conversion, which is another interesting channel to investigate.
Our administrators are the pillars of CAPP. They are making sure everything is done right the first time. You saw some of our work making critical contributions towards understanding the origin and fate of our universe. Our scientists are competing with the very best around the world and doing great. It's a lot of fun. I hope you've enjoyed the virtual tour and looking forward to your in-person visit to this exciting place. Thank you and be well.